Okay, let's get going. So, we were discussing series. And we learned about geometrical series, or geometric series. Which were a series of the form like this. So the most general form which we learned about was like this. K equals m to infinity, a r to the k. And the formula for this is a r to the m over 1 minus r. Okay. And we know that this thing converges if and only if r is within a certain range. What range allows this to converge? Yeah. So we're going to use this to calculate explicitly some series. So we've done one example of this. Let's do another. Example 6. Write 2.317 as a fraction. Okay, so 2.317 is 2.317, 17, 17, 17, and so on forever. So this bar above the 17 means that the 17 are repeated indefinitely. Okay, so now on, so when we have something like this, as it's written, it's got an infinite decimal expansion, but the question claims we can write it as a fraction. We can write it as one integer divided by another integer. Yeah, and obviously this is something to do with geometric series, so we have to try and figure that out. Yeah, okay, so let's look at this thing. Let's call this thing star. So, what is star equal to? It's equal to 2.3. And then let's think about what this 0.17 is, right? Because if we just take away the 2.3 and then add the next non-trivial thing, it is 0.17. Yeah? So 0.17, whoops. Did I say that wrong? It's 0.017. 0.017. What is this? This is equal to 17. If we divide it by 10, we'll have 1.7. If we divide it by 100, we'll have 0.17. So we have to divide it by 1,000 to get this. Do you see what I mean? Put this somewhere over here. So look at this. So if we just take, you could just figure out what you have to divide it by just by trying things. So if we just divide it by 10, and this is like 1.7, that's no good. Yeah. If we divide it by 100, that is 0.17. That's no good. So it has to be this. It has to be dividing something by 1,000. Yeah. So in order to get the first 3 digits, we have this 2.3, which we've put over here. And then if we add 17 over 1,000, we'll get these next 2 digits. Okay, everybody happy with this? Give me a thumbs up if you're with me. Okay, good. And then we want to get the next 2 digits after that, right? So we want to get these next 2 digits, yeah? And that's the same as adding 0.000 and then 17. That would give us these 2 digits here. You see what I mean? Yeah. So we need to come up with this as a fraction. So let's look. when we divide this by 1,000, we got this thing. We need it to be 2 decimal places to the right, so we're going to have to divide by another 2 digits here. Yeah? We're going to have to put another 2 digits right here. So this will have to be 17 over 100,000, like this. Yeah, because if we put another 0 here, we're moving it 1 to the right. Yeah, but we need to move it yet another 1 to the right. Yeah, so now we have to divide by 100,000. So it's going like this. Cool. And then we just continue, so that every time we want to get the next 2 digits, we have to put 17 divided by some number which has another 2 zeros from the last number. Yeah. So we keep doing this. And so on like this. Yeah. Cool. So this is starting to look a bit more like a geometric series. Yeah. Because we can write this as 2.3, and let's just factor out. Let's factor out 17 over 1,000 from here. So then this first number is going to be 1. This next number is going to be 1 over 100. This next number is going to be 1 over 10,000, and so on like this. Yeah? Cool. So can you see the geometric series emerging from this? What is the geometric series that we see emerging? What's the geometric series we see emerging? Come on. So this is the same as summing. Where do I start the n? Starts from n equals what? 0, perfect. Right? Because 1 is the first thing here. So we have 1 equals 0 to infinity of 1 over, and we need 1 over 100 to the power n. Yeah, like this. Because when n equals 0, we get this. When n equals 1, we get this. When n equals 2, we get this, and so on. Yeah? Everybody with me? Cool. All right. And now it's exactly a geometric series, yeah? So then we can just do this. So it's 2.3. Whoops. Since everything's over 1,000, maybe you want to consider writing 2.3 as over 1,000. So what would that be? That would be 2,300 over 1,000. And then plus 17 over 1,000. And then this is just the geometric series. We're just going to use our formula, right? So it's going to be 1 over 1 minus r. R is 1 over 100. Yeah? And then clean this up a little bit. 2300 over 1,000. What is this thing? 17. So this thing here will be 99 over 100. So if we have 1 over 99 over 100, that's the same as 100 over 99, right? So yeah. And that thing is a fraction, right? We're adding up 2 fractions. That thing is itself a fraction. And that fraction turns out to be 1,147. And this is non-trivial arithmetic to figure this out. If you have a question like this on the exam, obviously the numbers will be much easier so that you can just do this. But the principle is exactly the same. That we see this thing here, this line over these whatever digits, and then we write out what this means like this. This can be the tricky part. Yeah, so carefully write out how we produce this in this form. Okay, and then factor the best thing you can to make it as simple as possible. So the obvious candidate is 17 over 1,000. And then what you should be looking at is something that just falls out as a geometric series. And once it's a geometric series, then we have the formula. And that's it. So the hard part of this is just turning into something which looks like a geometric series. But once you're used to doing this, so there's several homework problems like this. You'll find that you quickly are able to turn something in like this into something like this, and then I claim it's quite straightforward. Are you feeling happy with this? Yeah? Cool. Okay. Let's discuss the following guy. This is a very different series. This is example 8. Consider this. The sum n equals 1 to infinity, 1 over n plus 1. Okay, so this thing isn't actually a geometric series. Okay, indeed, it's nothing like a geometric series. If we look at these terms, then for very large n, this thing is a lot like 1 over n squared for very large n, yeah? And 1 over n squared is decreasing much, much more slowly than a geometric series, right? As hopefully you can see. So if we put our numbers here on the real line, okay, and then if we just consider this sequence 1 over n squared, it's going down like this, and the function that recovers these elements of this sequence is 1 over x squared. Yeah? That's this guy. Whereas if we consider something like 1 over, say, any number, but let's just choose to the n, like this, yeah? Then what's the function that recovers this? So if this is an here, put it here, this is an is equal to this, then what function recovers this? It's going to be the function f of x is equal to x to the minus it's going to be r to the minus x. Right? Just 1 over r to the x. Yeah? And this thing is an exponential function. This is an exponential function, which is extremely fast decreasing. So for example, if we had 1 over e to the n, right? Then the function that recovers this is f of x is equal to e to the minus x, right? Which is going down incredibly fast, way faster than 1 over x squared. Yeah? So this geometric series stuff here is converging, is a sequence of points that's going to 0 way, way faster than these guys. And the reason it converges is very different. And we'll talk a lot more about this going forward. But this is just a little hint of what we're going to start to consider. The reason some of these series converge is because the terms we keep adding are smaller and smaller and smaller fast enough. And this guy will converge, but for not anywhere near the same reasons, because these guys are going to 0 so much more slowly than this guy. Okay, so no geometric series structure here, nothing like this. We're going to have to do some algebra. So I'll look at this. So 1 over n to the n plus 1. We can consider this like this, as a over n plus b over n plus 1. Okay, just from our knowledge of partial fractions. And then we can just figure out what these coefficients are. A plus b is equal to 0. because if we factor out the n, we have a plus b times n is equal to 1 for all n. If a plus b was not equal to 0, that's just impossible, right? That's just impossible. No matter how small a plus b would be, if we have a plus b times n is equal to 1 for all n, it's impossible. Yeah? Yeah? See what I mean? So that has to be the case. And we also have that a is equal to 1 because since we know that a plus b is equal to 0, then the only thing remaining from this equation is just that a is equal to 1. Well, actually, we don't even need to do it that way. We just compare the constant terms. So let me not rush through this. So from this equation, just like in partial fractions, we have two equations. We have this equation that a plus b is equal to 0, just comparing the term in front of the coefficients in front of the n, and we have that a is equal to 1. So we're comparing the first order term. So previously, this would be corresponding to when we have x here instead of n. That's when we consider the linear term. And the constant term is just a is equal to 1. That's what we're doing. Does this seem familiar to you? So we have this is true, which allows us to conclude that b is equal to minus 1. So indeed, we would not get the same answer if I made that mistake or continue to make it. So then this thing now becomes, let's just put it in here before we clean the board. This just becomes 1, and this is minus 1. Okay? Yeah? And that thing is going to allow us to understand what this thing is. Okay? So I'm going to clean the board. While I do this, using this, try and figure out what this sum is. And the hint is to use partial fractions. Start again. The hint is to use partial sums, because we know that this thing only makes sense as the limit of the partial sum from n equals 1 to capital N. Yeah? So write down the partial sum of this thing with the fact that we can represent 1 over n times n plus 1 as 1 over n minus 1 over n plus 1. Write down the partial sum from n equals 1 up to capital N, and see if you can make sense of that expression. Okay? And then we'll do it together, and we'll see what we get. All right, so what did we get? We were summing this thing, n equals 1 to infinity, 1 over n plus 1, and we know that 1 over n plus 1 is the same as 1 over n minus 1 over n plus 1, like this. Yeah? So, this guy here, the guy we're trying to understand, this is the limit as capital N goes to infinity of this thing, of the sum from n equals 1 to infinity of the partial sums, right? This is n equals 1 up to capital N of this thing, which we're now going to write like this, 1 over n minus 1 over n plus 1. Yeah? That's the meaning of this. This has no other meaning except as the limit of these partial sums from n equals 1 to capital N. That's what we discussed, yeah? Cool. So if we look at this thing, so consider this thing, the sum from n equals 1 to capital N, 1 over n minus 1 over n plus 1. What cool thing can you see happening here that allows us to get somewhere with understanding what this expression is? Right. If we write out these things, so let's write out this side of it first. Right? Let's write out this side of it. Yeah. Then what do we have? We have 1 plus 1 over 2 plus 1 over 3 dot, 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 all the way to 1 over capital N. And now let's write out the other side of it. Sorry for this mess I'm making here. Bad board management. So if we write out the other side of it, which is this part right here, the sum of minus 1 over n plus 1, what do we have? We have minus 1 over 2, minus 1 over 3, minus 1 over 4, all the way minus 1 over n, minus 1 over n plus 1. Yeah? Everybody see that? Cool. And then we have a massacre, right? So we have this thing is killed by this thing, this thing by this thing, this thing by this thing, this thing by this thing. The only survivors of the massacre are the two terms, this one and this one. Yeah? Yeah? So this all becomes very conveniently just 1 over n plus 1. Why are we so happy with that? Why does that make us happy? So that quicker, yes. So look at this. The limit as capital N goes to infinity of this expression, sum n equals 1 to capital N, 1 over n minus 1 over n plus 1. Then by what we've just learned, that's exactly the same as the limit as capital N goes to infinity of 1 over 1 minus 1 over capital N plus 1, no? And then this thing, as capital N goes to infinity, this thing goes to 0, right? And this thing is just constant, so this is just equal to 1. Yeah? Cool. All right, so we can explicitly calculate this series. And this series is called the telescoping series because, as you just saw, this complicated expression just telescoped down into just two terms, or it telescoped down into just these two terms. Yeah? So this is called a telescoping series. And this kind of series, the telescoping series and the geometric series, are the only two series that we can explicitly calculate at this point. Later we'll learn something called Taylor series in many weeks going forward that will allow us to calculate some other ones. But for now, for quite a number of weeks going forward, the only two ways that we can explicitly get an answer from a series will be either because it's a geometric series or it's a telescoping series. Okay, so underline this in your mind, because whenever you see a question that says, what is the sum of blah, blah, blah series, then you have to be looking at a geometric series or a telescoping series. Yeah? And therefore, you have a good advantage in solving that question, because you just have to identify which it is. So the previous example, you have to identify that this, whatever, 2.317 line is a geometric series, and then you can get the answer, right? So sometimes it seems a little bit disguised how what you're looking at is a geometric series or a telescoping series, but those are the only two things where we can explicitly calculate the answer. So if you learn to calculate the answer from the geometric series, just a formula, or the telescoping series, which is this trick, you can do every question of the kind, what is this series equal to? Let's do another one. So this is connecting with what I said about the growth or the how quickly the terms of the series are decreasing. Let's consider this thing. This is example 9. What about this? Okay. Any ideas about this guy? Is it a geometric series? Right. So a geometric series will be something like this, right? It'll be some number to the power n. Yeah? We don't have a power term exactly as you say, so it's not a geometric series. Yeah? Yeah? Maybe it's a telescoping series, but actually it's not. Actually, it's not. There's going to be no way to do this kind of stuff. A telescoping series, we're always going to have something like this, where we can break it up into something and then the next guy, so that there'll be a whole bunch of cancellations. You know? So it's not actually a telescoping series either. It is a harmonic series. I don't want to. Okay, so the term harmonic series is just a name for this, but So I'm trying to avoid introducing too many names. But yes, this guy is called the Harmonic Series. Yeah. So we can't use any of our methods to actually understand this. What's our next thing? What's the next natural thing to try and do? What do I keep telling you to do? What's the yeah, but there isn't any method to do it, since the only way we can sum the partial sums is if it's geometric or if it's telescoping. What's the mantra of this course? What do I tell you every lecture at least 3 or 4 times? Yeah, draw a picture, visualize this thing, visualize the math, huh? So let's do that. So if we consider these guys here, the sum of all these guys, this is how we started to talk about series. We can think about this as the area of all these blocks, right? So the first block is from 0 to 1, and it's got height 1, like this, right? The next block is from 1 to 2, and it's got height 1/2, like this. The next block is from 2 to 3, height 1/3, and so on like this. Yeah? Yeah? Cool. All right, so looking at this thing, then this sum is the area of all of these blocks going off to infinity. Right? If we add together all of these blocks going off to infinity, that thing is the same as this thing. Yeah? Cool. All right. And this thing converges if the area of all of these blocks summed together is actually finite. Yeah? Okay. So, do you believe that the area of all of these blocks summed together is actually finite? You'll sound like you're saying the right things. Can you elaborate? So not a divergent function, but a divergent what? Yeah, not... The sequence, divergent integral, the sequence for sure is going to 0, yeah? But if we try and understand this in terms of something else, the natural thing would be to try and understand this in terms of the graph of a function that recovers something like this, yeah? Yeah? So, if we did the function that recovered this sequence, so if we have if we find f such that f of n, let me write it as a sentence. So, find f such that f of n is equal to 1 over n, then the f that does that is what? What f does that? What f does it? Yeah. So if we have the function 1 over x, then it exactly goes through the corners of all these blocks like this, yeah? Like this, yeah? So if we think about the area underneath the graph of 1 over x from 1 to infinity, we know what that is, right? Integral from 1 to infinity of 1 over x is indeed a divergent integral, right? The antiderivative is log, yeah? And we just take the limit as r goes to infinity. We know how to do this. This is a divergent integral. The area underneath the graph of this function is infinity. Yeah? Cool. And the reason that's the case is because 1 over x is not going down fast enough towards infinity. Start again. 1 over x is not going down fast enough to 0 as x goes towards infinity. Yeah? Cool. All right. So based on the fact that the picture of the graph of 1 over x and these blocks look kind of similar, we can start to anticipate that actually the sum of the areas of all these blocks are not going to be finite. But we don't have a proof from this because the graph lives on top of these blocks. Yeah? So if we had a graph whose area underneath it was infinite, but it lived underneath the blocks, yeah, then we would be able to show definitively that this thing does not sum to any finite number, that this series is divergent. Do you see what I mean? Yeah? Cool. All right, maybe my picture's a little bit small. Let's blow up the picture a little bit. So then this is 1, and this is a half, and this is the next guy. So this is 1, this is 1 over 2, this is a third. Yeah, next guy is a quarter. So I'm not drawing this very accurately because I don't want to have two smaller blocks. So what we'd like is to find something that goes underneath these guys like this. Yeah? And if we knew that the area underneath the graph of the guy that goes underneath the blocks is infinite, then we would know the thing diverges. Yeah? So, looking at this, can you think of a function that would do this for us? Can you think of a function, let's call it g, better if I did this in blue. Don't know if that changes anything. Can you think of a function that will do this, that will create this picture here? Well, actually it would, but this guy's going to 0 too fast, and that won't show what we expect to be true because the integral of 1 over x squared will actually be finite. So yes, it did go underneath, but we want it to go underneath and still have infinite integral. What would do this? What function would give us this here and this here and this here as I've drawn it? So we can just look at the picture, look what you need. You need g of 1 to be 1 over 2. Yeah? You need g of 2 to be 1 over 3. You need g of 3 to be 1 over 4. We're just writing down in the language of math what we want from this picture, right? As always, this is a language that helps us describe pictures. This meaning is the pictures, yeah? So what function does something louder? Perfect, yeah. That would work, yeah? That would work. So this function here is underneath all of our blocks, yeah? And if we integrate from 1 to infinity, 1 over x plus 1 dx, this thing too is divergent. We can just change variables, and that thing is the same as the integral from 2 to infinity, 1 over x dx. Just do a u substitution. Actually, let's call it u, since we're implicitly doing a u substitution. And that thing is infinity, yeah? And that answers our question, because for sure this function's underneath, and for sure the integral of this function from 1 to infinity is equal to infinity. It's divergent. That means this area that lives underneath all of our blocks from the second block onwards is infinite. So the sum of all the areas of the second block onwards is infinite, so the sum of all the blocks is infinite, yeah? You see what I mean? Cool. So this is a key point. When we're having a series, then its convergence is related to how fast the terms that we're summing go down to 0, or at least when we have a series of positive terms. So series does not converge however, when we had the series, this guy, 1 over n times n plus 1, this thing is only going to 0 a little bit faster. But that does converge. So if you are someone who lived for an infinity of time and you wanted to take a long walk, but your step sizes got smaller and smaller and smaller, if you kept taking step sizes getting smaller at the rate of 1 over n plus 1, start again, 1 over n times n plus 1, then you could do your infinite sequence of steps and you would just be exactly 1 whatever meter away from where you started at the end of infinity. Yeah? But if you are someone who lived for infinity, wanted to take a walk, taking smaller and smaller steps, but you took slightly less quickly decreasing step sizes. So instead of having your step size decrease like 1 over n times n plus 1, if your step size decreased like 1 over n, even though you're getting very quickly to having very, very, very small step sizes, your step sizes are not going to zero fast enough, and you'll actually end up in infinity. You'll be going forever if you make this walk with your step sizes decreasing at the size of 1 over n. Which is kind of counterintuitive, right? If you had some very smart, say, 12-year-old nephew or niece, and you set them this kind of thing as a paradox or as a puzzle, and you said, imagine a man walks forever taking step sizes, but each step he takes is getting smaller. In fact, the nth step has got step size 1 over n. Will that man actually walk to infinity, or will he stop somewhere? That would be quite a tricky thing to figure out, right? If you are not a mathematician, you'd really struggle to answer that. The question is clear, right? Yeah, but actually answering it is pretty difficult, pretty unclear. If you look back at the history of math, this is the kind of thing people actually did. They actually discussed these kind of questions quite a lot, and were not able to answer them because they didn't have this kind of tools to actually answer them. But because of modern means from the 17th century, modern mathematics, we can actually answer this because we can figure out that taking this collection of step sizes is actually something which is going to be less than the integral of this function. And because of the fundamental theorem of calculus, we can actually explicitly integrate this function. Yeah, so we're actually using non-trivial deep theorems to answer this. So because of this ability to calculate this integral, we can answer the question that this man taking his step sizes of size 1 over n will actually end up at infinity, whereas this man taking his step sizes of the size 1 over n times n plus 1 will end up at a finite place just 1 meter ahead of where he started. Yeah? Yeah? So this is power. This is power to be able to do this. And these are ridiculous examples. No one lives forever and no one's going to take an infinite sequence of steps going forward in smaller step sizes. But there are many situations where this is exactly the situation that is happening, that we are summing something over and over and over again, and we don't know when it stops. Yeah? So, for example, if you take your computer and you write a little algorithm to add 1 over n, then you'll type that in and you'll get an answer out. You'll get an answer out and you'll watch your answer come out. It'll look more and more like the answer is converging to something. The decimal places will stop changing, will seem to slow down, and you'll think, okay, well, the answer is something, something, something. But that's not what's happening. What's happening is your computer's RAM is filling up and it can't deal with these very, very small sums. Yeah. In fact, this is a good test about how powerful a computer you have. The more powerful a computer, the bigger number it will get to before it seems to slow down, to converge to something. Yeah. In the early days of computers, people were very excited that they could try and calculate anything, and they would do things like that. They would try and come up with an answer to something which involved doing an infinite sum of terms, but they wouldn't have a mathematician on board to tell them whether or not the answer would make sense. And they would sum a sequence of terms like this that sums to infinity, and the computer looks like it gives an answer. And they'd go, oh, very happy, okay, we can do this thing because the answer is this. But the answer was nothing like this. The answer was actually infinity. They just didn't know what they were doing. They had no conception of what it meant to sum a series that doesn't converge. Which is why we're not messing around with this. This is not some kind of intellectual game that nerds like myself just get into. This is something that allows you to correctly calculate quantities you need to build a technological world. Which is why you people, mostly engineers, are learning this stuff. Most of you will be using software. But if you don't actually have some idea what the software is doing, then you could easily do something like this. You could easily sum 1 over n and then think you've got an answer and build your bridge based on the answer, and then the thing collapses. Or your space shuttle or whatever thing you're building, knowing why this stuff actually comes to an answer as opposed to not giving an answer is not a game. It's not a joke. It's not an academic exercise. This is the real stuff. This is the real stuff you need to know. All right. So we have two main takeaways. If we don't go to zero fast enough with 1 over n, like for example 1 over n, then the sum is divergent, but just a little bit faster it does. A little bit faster it does. And as we learned just from the beginning, this thing is called the harmonic series. And it's a key example to understand going forward. It's a key example in exactly the same way the function 1 over x is a key example about divergent integrals of type 1. Okay, let's do this theorem. If the series goes 1 to infinity and converges, then the limit times n goes to infinity, an is equal to 0. Okay, think of the metaphor I just gave you of taking steps, okay? And an is your step size. And this doesn't require that the an are positive, but just to make it simpler, just think about an being positive. Tell me why you believe that this is true. Oh, goodness, I've overrun. Sorry. If you need to leave, please leave. I want to keep talking about this topic. You can watch on video everything that we're going to do. I'd like to finish series today so that I can talk about the practice exam on Monday. So look at this. Think of the metaphor of a sequence of positive terms being equivalent to step sizes. Why is it the case that if this thing converges, which means we're taking step after step after step, and ultimately we end up in a finite place, why does that mean that the sequence of steps has to converge to 0? Okay, sounds like you're coming towards the right thing. So we're gonna figure this out by doing something called arguing by contradiction. So we're going to suppose that this is not true. So suppose we have a sequence of steps, which we do from infinity, that comes to a finite answer. But every now and again, we suppose this isn't the case, or the limit is not equal to 0. That means every now and again along our sequence, we have a guy which is not close to 0. Maybe it's very small. So if this sequence is tending down to 0, right, then supposing that's false, then that means that there's a collection of these elements that are actually not like 0. Maybe they're very small. Maybe they are bigger than 0.0001. Okay? But if it's not tending to 0, if the sequence is not tending to 0, let's draw the picture of the sequence, right? So if the sequence, just imagining its positive terms, if the sequence is not getting trapped close and closer to 0, that means as we go along, every now and again, there's a guy that's bigger than something. Yeah? Might be a very small thing, but every now and again, maybe it's very rarely, there is a guy that's bigger than something. Yeah? So that means maybe the term a to 100 is bigger than 0.1, and then the term a to 1063 is bigger than 0.1, and then a to 1,749 is bigger than 0.1, and so on. It doesn't matter how rarely these guys occur, but as we go off towards infinity, there's always some other guy that's going to be bigger than something. Say 0.1. All right, so imagine you're the guy doing this infinite collection of steps. Yeah? And suppose you do a step every 10 seconds. Yeah? Then every now and again, you'll do a step which is bigger than 0.1. And maybe the times between these 0.1 size steps is very long. Maybe it takes 100,000 years between the last 0.1 size step and the next one. Yeah? Tell me what's going to happen if you're that man who, walking forever, every now and again, will take a step of size 0.1. What will happen? Okay, but so what we're doing is arguing by contradiction. So we have that the assumption is that it converges. And I'm saying, let's suppose it doesn't tend to 0. And then we're going to get a contradiction out. Okay? So I understand what you're saying, but we're gonna order our thoughts in a different way. So we're assuming that we end up in a finite place, and we're arguing by contradiction, saying, but suppose every now and again we take a step size of size 0.1. Are these two things compatible? So you're the man taking your 0.1 size step every now and again, once whatever infrequent period you're doing it, as time goes forward, you know that you'll always eventually take another 0.1 size step. Maybe it'll take you 100 million years, but you'll always eventually do it. What happens to your journey if that's what you're doing? So by the time as you go towards infinity, how many 0.1 size steps have you actually taken? An infinite number of them. So how far have you got? Infinity, right? So if every now and again, doesn't matter how infrequently, you take a 0.1 size step, then you're never going to stop moving forward towards infinity, right? And ultimately, at infinity, after you've done this for an infinity amount of time, you will be at infinity yourself. You would have traveled an infinite distance. Do you see what I mean? Yeah? So if the assumption is that you're not traveling an infinite distance, that the series actually converges, then it can't be the case that every now and again you take a 0.1 size step. There has to be some time where you stop taking 0.1 size steps. Yeah? Maybe it has to be a long, long time. Maybe after 100 million trillion years, you've taken your last 0.1 size step. But if you're actually going to converge to an answer, there has to be a time when you stop taking 0.1 size steps. Do you see what I mean? Think about it for a second. And I'll ask again if that makes sense to you. Draw a picture of the progression of a guy who every now and again keeps taking 0.1 size steps and will never actually stop taking them, even though they are very, very infrequent. So, is the metaphor making sense to you? Do you believe that if the journey comes to a finite total length, that ultimately you stop taking 0.1 size steps? Does that make sense to you? Give me a thumbs up if you're with me with that. Okay, good. Now, since you agree that ultimately you stop taking 0.1 size steps, you're also going to agree that ultimately you stop taking 0.01 size steps for the same reason. Yeah? And eventually you're going to stop taking 0.0001 size steps. Yeah? Yeah? So in fact, the only way that can be the case that your journey is going to be finite is if your step size goes down to 0. Yeah? There has to, no matter how small a size you want, there has to be a time where you stop taking steps of that size. You'll never take another step of that size. Yeah? Now, in the language of math, that's exactly saying that the limit of these terms, an, is equal to 0. Because these an are our step sizes. Huh? Cool. So what we've just shown is that we have a contradiction from the assumption that the limit of an is not equal to 0. Yeah? So that means that the sequence an must tend to 0. So we've just understood that if the limit as, whoops, wrong order of terms. If the sum n equals 1 to infinity an converges, then the limit as n goes to infinity an is equal to 0. That's what we've learned. Okay? And this too is very powerful because this allows us to quickly identify when things fail to converge. So this is called the divergence test. So suppose the limit as n goes to infinity an does not exist, or the limit is not equal to 0, then the series we create out of these terms does not converge. And this is just a rephrasing of what we've learned before. This is what we call the contrapositive. Okay? So we have that statement A, this thing converges, implies statement B. Yeah? So that means that not statement A implies not statement B. It's called contrapositive. Okay? So if we have that this thing either does not exist or does not converge to zero, then the series does not converge. Okay? And here's an example of how we use this. Look at this example. Consider the sum n equals 1 to infinity n squared over, let me write that better, n squared over 5n squared plus 4. Does this converge? What's your answer, people? Tell me why. Because the limit is 1/5, right? No. The limit as n goes to infinity of n squared over 5n squared plus 4, as you all know, is just 1 over 5. Yeah? So these step sizes that we are taking come closer and closer to the number 1 over 5. So what we are doing in this series is we're taking this infinite sequence of positive steps of step size 1/5. Yeah? And of course, that thing is going to take us to infinity. Yeah? Cool. All right. Let's see what else. Okay. I want to do just the limit laws, and then I'll wrap it up. So, this is called the divergence test. It's very, very useful. You can quickly get the answer to series that look maybe plausible that they might converge, but just considering these terms right here, asking yourself, does this thing actually converge to zero? And if it doesn't, then for sure the series cannot converge. Yeah. All right, let's talk about limit laws. So what is good about series is that, well, one of the things that's good about series is that they behave just like finite sums with respect to algebraic manipulation. So given convergent series, the sum n equals 1 to infinity an, and the sum n equals 1 to infinity bn, then if we consider this series the sum from n equals 1 to infinity an plus bn, that is just the sum of both of these guys. Just like a finite sum. Yeah? The same if we subtract series. And if we have some lambda, like this, yeah, then that is the same as just pulling out the lambda from this thing. These things follow just by the definition of series, just because it's true for a finite sum, and the series is the limit of these finite sums. So this is really easy to see, like this. Okay, so we can use this to figure out some series. So here's an example, example 11. Look at this. The sum from n equals 1 to infinity of 3 over n to the n plus 1 plus 1 over 2n. Okay, so as written, this is neither a geometric series or a telescoping series, right? This thing here is neither of these two things. Yeah? However, because of this stuff we've just seen, this thing, let's call this thing star, is the sum from n equals 1 to infinity of 3 over n to the n plus 1 plus this thing, the sum from n equals 1 to infinity 1 over n to the 2. Yeah? And because we know we can just pull out a factor, this is the same like this. And then this guy is just a geometric series when it starts from n equals 1. So this guy is a half 1 over 1 minus 1 over 2, just using our formula for the series. This guy we've seen before. This is the telescoping series that we did before. This thing sums to be equal to 1. Yeah? So this entire thing is just 3. And what's this thing? This is a half, and we have 1 over 1 minus a half, so that's 1 over a half, which is 2. So that's a half times 2, which is 1. So it's 3 plus 1, which is equal to 4, and that's our answer. Yeah? Cool. So the fact that we can just consider the sum of terms like this as two separate series means that we can deal with expressions like this really easily. So when we're talking about integration, I said that integration was this more sophisticated version of addition that allows us to add infinitely many things. This is another more sophisticated version of addition, but it's adding another version of infinity. This is something called countable infinity. This is infinitely many terms that we can put in a list where it goes 1, 2, 3, 4, 5, 6, so on. Yeah? Whereas integration is an addition over infinitely many terms that we can't put into a list that we can label 1, 2, 3, 4, 5. That's called an uncountable infinity. So integration is like adding everything of the form f of x for x between two numbers, say a to b. If we try and add all of these numbers for every x between a and b, that's integration. This thing, series, are adding an infinite sequence of things, a1, a2, and so on. Yeah? But if you think about all of these numbers, this is an infinity of numbers, but it's a bigger infinity than this infinity of numbers. Yeah? So what we've learned is yet another more sophisticated way to do addition, and all the things we know about addition hold true for this more sophisticated thing. So we have the same thing holds true for integrals, well, this holds true for series. Yeah? So we have we have a different, more generalized version of addition in this thing of summing series. Yeah? Cool. All right. So sorry I overran. Thank you for your attention. If you have any quick questions, ask me now. Otherwise, I will see you all on the week. I will offer, by the way, a weekend review session. If 8 or so people are interested to do this, I will hold a session on Sunday afternoon where I'll answer any questions you want. I'll send an email. If you're interested, send me confirmation. And if any quick questions now, I can take them. Otherwise, see you later.